Okay, so now let us move to the case where the domain has the dimension at least 3. So in this case, we get similar results, but the energy concentration set, instead of being points, they are now codimension 2 objects. And so in 3-dimensional domains, they could be curves. And you can ask what extra structure or extra properties they have, more precisely geometric properties. And in various situations, we know that the energy concentration set actually has the structure of a minimal submanifold, at least in the sense of geometric measure theory. So there's a long line of results of this type. Among the earliest such results are the work by Gerard Sonner and Lynn Rivière. And then perhaps more relevant to the statement I'm going to give below is the result by Betuel-Prezis and Orlandi from 2001. So they study solutions to the Ginzburg-Landau equation on simply connected domains in Rn, subject to some Dirichlet boundary condition. And they show under natural energy bounds. And I'll elaborate on that in a moment. They show under natural energy bounds that the sequence of solutions exhibits energy concentration along a codimension 2 set that supports, again, a minimal submanifold in the sense of geometric measure theory. Later, there are refinements by Betuel, Orlandi, and Smets, who also studied the parabolic setting, in fact. And then using slightly different methods, Alberti, Baldo, and Orlandi, they studied a slightly more general class of functionals where you replace gradient squared in the definition of the Ginzburg-Landau functional by gradient to the p power. Okay, but results like this these important results are the starting point for this whole discussion about the relationship between the Ginzburg-Landau functional and codimension 2 minimal submanifolds. And then you can ask how far you can push the analogy and what results in one field tell you about the other. Okay, but for now, let me give you one statement of this type, just to give you a flavor of what I'm talking about. So this one works on a closed Riemannian manifold and is due to Daniel Stern and independently myself. Oh, by the way, Daniel Stern is also speaking at this workshop, and I encourage you to also check out Daniel's talks. He's going to focus on a slightly different approach. But I hope together our talks would motivate you to explore this very interesting direction. So suppose we have a closed Riemannian manifold. And with first Betti number 0, I'll say something about that in a moment. And suppose for each epsilon you have a solution to the Ginzburg-Landau equation with parameter epsilon, satisfying the following energy bound. So their energy divided by log epsilon is uniformly bounded. Then, again, as epsilon goes to 0, up to choosing a subsequence, if you take the Ginzburg-Landau energy densities of your solutions and normalize them this way, then as measures on the manifold, they converge to this mysterious double bar V. Okay. I'll explain what this is below, but for now, I'll give you its name. It's the weight measure of a stationary rectifiable n-2 varifold. Of a stationary rectifiable n-2 varifold Okay. Now let me make a couple of remarks about the assumptions. We assume the first Betti number is 0 to rule out an absolutely continuous part in the limit. So in general, if you drop this, then, so if you drop the Betti number 0 assumption, then there would be another term, a second term here following the weight measure, whose precise form I don't want to write down. But it's up to a factor, it's the norm squared of a harmonic 1 form times the volume measure. That's why I say it's absolutely continuous. And of course, if the first Betti number is 0, there can be no non-trivial harmonic 1 forms. So that term is not there under this assumption. Okay. Now, secondly, this energy bound. If you go back to the statement of the theorem by Ellipticity and Alain, you see that if you look at the conclusion, you see that this energy bound follows. And in fact, on their way to proving their theorem, they had to derive this bound first. Whereas here we have to put it as an assumption. The difference is, in their case, they could use the boundary data to construct comparison maps and force this bound onto their minimizers. Here, on a closed manifold, you can have solutions which violate this bound. For example, the zero function. It's a solution to the Ginzburg-Landau equation, but its Ginzburg-Landau energy, if you recall the definition of the functional, would be proportional to 1 over epsilon squared, which is much bigger than log epsilon, of course. And in the case studied by Ellipticity and Alain, such solutions are not admissible because their boundary values always have norm 1. Okay, so in any case, here we have to assume this. And I hope I have convinced you in the remarks after theorem A that this is a natural energy bound to assume. And in fact, thanks to Daniel's work, we know that you can find solutions satisfying, you can find a sequence of solutions satisfying this energy bound and giving you a non-trivial limit as epsilon goes to 0. So this assumption is really not that bad. Okay, but here's the statement. And I think I owe you an explanation for the blue words. I will not give you the formal definition of varifold because if you are already familiar with them, then I'll be wasting your time. And on the other hand, if you haven't thought about them often enough, then I wouldn't be doing you much good in this limited space I have over here. So I'll just give you some ways of thinking about them. So a varifold is like a submanifold in a measure theoretic sense. You can integrate functions against them. When you have a diffeomorphism of the ambient manifold, you can use that to push them forward. And you can assign a volume to them, etc. Rectifiability is a kind of regularity condition. So you can think of rectifiable varifolds as what, in a very loose sense, what Sobolev functions are for PDE theory. You need these things to build a satisfactory existence theory for critical points of the volume. But anyway, this rectifiability condition in particular implies that your varifold has a tangent space almost everywhere. The weight measure pretty much tells you where your varifold is, and you can think of it as the n-2 dimensional Hausdorff measure restricted to a submanifold. And finally, being stationary is pretty much just being minimal. To elaborate a little bit on this last part, recall I just said that you can push varifolds forward by diffeomorphisms. So if you take a vector field on M, let's call it X, it generates a flow. You use that flow to push your varifold forward, like you would as if it's when it's actually a submanifold. You compute the volume, which is just the total mass of the weight measure, and differentiate it at time equals 0. That gives you the first variation formula of the volume. It's a functional acting on vector fields, and it's just integration over the support of the weight measure, which I'm calling sigma, of the divergence of the vector field along the tangent spaces, which exist almost everywhere, against the weight measure. In the case of a smooth submanifold, smooth closed submanifold. In the case of a smooth closed submanifold, by splitting X into its tangential and normal part along sigma, and using divergence theorem and the definition of the second fundamental form, you can see that this is just the normal part dotted with the mean curvature. Stationarity is just a requirement that the first variation vanishes for all vector field X. And you can see from this line here that it coincides with the vanishing of the mean curvature when your varifold is just a smooth submanifold. So stationarity generalizes minimality in this sense. Okay, and so that's why you can view this result and all the results I cited above. That's why you can view these. And also, this result here as saying that under suitable conditions, critical points of the Ginzburg-Landau functional give you critical points of the volume via energy concentration. One more technical remark, and then I'll try to describe the main ingredients for the proof. So we don't know whether this stationary rectifiable varifold has integer multiplicity. In some special cases, for example, for minimizers, in the setting that Lin and Rivière studied, they could show that it's integral. But in general, we don't know, and that's still an open question. So now I will attempt to describe the main ingredients for the proof of this theorem. It follows closely the result of the arguments of Betriel-Quizzes and Orlandi from 2001. And actually, many of the analytical tools are based on the work of Betriel-Quizzes and Alain from the mid-90s. So the first theorem I mentioned. So the main ingredients. Okay, so it follows, among others, Betriel-Quizzes and Orlandi very closely, and with tools from the two-dimensional case, analyzed by Betriel-Quizzes and Alain. I guess I should also apologize for my French pronunciation. I'm sorry, it's not perfect. First is a monotonicity formula. This is very similar to other geometric PDEs, for example, harmonic maps, where if you take the energy, in our case, it's the Ginzburg-Landau energy on a ball, let's say of radius r. You normalize it so that it's scaling invariant, and then you multiply by a correction factor that accounts for the fact that we're on a manifold, so the metric is not flat. Then you get a non-decreasing function in the radius. Oops, I forgot the scaling factor. Okay, for all r less than r below some threshold. So it is telling you that if when you go to smaller scales, things do not get worse. Do not get worse. And the next ingredient is what's called the anti-ellipticity theorem in this context. But in other contexts, for example, harmonic maps or Yang-Mills connections, it's usually called an epsilon regularity theorem. But for us, epsilon is already used. But anyway, it says that there exists a universal constant eta naught positive, such that if the rescaled Ginzburg-Landau energy on a ball of radius r of your solution is small compared to log epsilon in a scale invariant way, then when you pass to the ball of half the radius, you get the following mean value type inequality. Sorry, I realize I'm not writing big enough. Pointwise bound on the energy density in terms of the integral, normalized. Okay, so this bound together with the equation allows you to get higher order estimates, where the energy does not concentrate in the sense that it's small on one scale in a scale invariant way compared to log epsilon. And these higher order estimates allows you to pass to a smooth limit and obtain the harmonic one form that I mentioned when I explained the Betti number assumption. So at this level, you prove that it's possibly there, and then you use the Betti number assumption to show that it's not there. Okay. But what we're really interested in is the part where energy concentrates. So 1 and 2 together allows you to locate where your submanifold is, so to speak. By the assumption, the energy bound, you see that this sequence of measures has uniformly bounded mass. And so you can pass to a weak star convergent subsequence to some limit mu. Now by 1, the monotonicity formula, the n-2 density exists everywhere. And by the Anti-Ellipticity Theorem, you can actually show that this density is either zero or above a certain positive threshold. Or it's above, sorry, a certain positive threshold. And what matters is that this is a definite positive lower bound. So the support of your weight measure, namely your submanifold, is actually given by the place where this density is positive. Well, there's no x. Okay. You can show by a covering argument that this has finite n-2 Hausdorff measure. So it's indeed a codimension 2 set. And now you have to say that this is a minimal submanifold, or this varifold is stationary and rectifiable, more precisely speaking. And for that, we have to use the equation in a slightly different way. So stationarity involves vector fields on M, if you recall. And so we have to make vector fields enter the picture. And we do that by testing the Ginzburg-Landau equation against the directional derivative of the function, again, along the vector field. This has the same effect as computing the following derivative. Wait. It's going crazy. Same effect as computing this. Where you take U and compose it with the flow generated by the vector field. So phi t is the flow of x. Okay, but in any case, you do this, and you get this formula. Now, if you recall the first variation formula for the varifold, right, this integrand, you can actually write as nabla x paired with orthogonal projection onto the tangent space of your varifold or of your submanifold. And so this condition here is telling you that something is stationary. And indeed, when you divide by log epsilon and pass to the subsequential limit, you get a stationary generalized varifold. And by the theory for these objects developed by Ambrosio and Sonner, you can show that these are, in the limit, these converge. These matrix-valued functions indeed converge to orthogonal projections, and so you get a genuine varifold. And then the lower bound up here, together with Allard's rectifiability theorem, tells you that you'd get a stationary rectifiable varifold. Okay. So basically, ingredients 1, 2, 3 tells you where your submanifold is supported at, and then in step 4 you have to build a stationary rectifiable varifold, or you have to build a minimal submanifold over that set. And that's roughly how the proof goes and what goes into it.